Functions of two or more variables. So everything we've done thus far, really in all mathematics, is like y equals f of x. One independent variable, one dependent variable. Now we're going to get into more. And the rules get a little different. So we're just going to start with like a function that we're going to call z that's a function of two independent variables, x and y. X and y can be whatever they want within reason. Whatever x and y are determines what z is. So that's how we write it. Instead of just writing y equals f of x, we write z equals f of x comma y. So graphically, a function of two variables is going to be a 3D graph. So I'll show you a little bit of 3D graphing, but unless you're really in a legit Calc 3 course, you would get a lot more into 3D graphing, and I would make you do some and show you. Without like moving these graphs around, it can be hard to tell what exactly you're looking at. And also you have to have, obviously your TI calculator can't do this, so you have to have some special kind of software to make them. So what we do to graph these things is we take the normal XY plane, which looks like that normally. It's two-dimensional. We lay it down flat. And then to add a third axis that just sticks straight up called the z-axis. So the vertical axis is now the z-axis and the xy plane lays down. So now we have a three-dimensional coordinate system. So here's a graph of a function of two variables. There you go. That's the graph of z equals x squared plus y squared. It's called a paraboloid because it's like a parabola that goes all the way around, right? So in this picture, the red axis would be the y-axis, the green axis would be the x-axis, and the one sticking straight up, the blue one, would be now the z-axis. So the z is only ever going to take on one value for each pair of variables x and y. In other words, that's called a surface now instead of a curve. That surface would pass a vertical line test. So it's cool to look at this stuff. But picturing it in your head's a lot harder. And to be honest, for this class, we don't even really need to get into graphs at all. So I just want to show you this is how we would theoretically depict a function of two variables. We don't really need to picture it. We just want to use them. Again, that would be a function of two variables. And now I'm asking, okay, what's the domain of that thing? It has a domain just like any other function. The domain of the paraboloid that you're looking at is just everything. What about this thing? Well, what do you know just looking at it? 4x minus 2y can't be 0. Right? And that's the only thing. The denominator still obviously can't be 0. So to kind of visualize that, the 4x minus 2y equals 0 can be rearranged like that. Y couldn't equal 2x. And so if you ignore the z-axis and just look at the xy plane, which is the flat one, and picture the line y equals 2x, it's not a line anymore, it's a plane. But if we were to look at the graph of x squared y over 4x minus 2y, it would not be defined anywhere on that plane. So now instead of just like a little interval where the domain isn't defined, we have like an entire region of the plane where the function isn't defined. So domains work the same way. You still can't divide by 0. Sure. So if you ever have to get more into this, I'm using this free software I'm sure I've talked about before called GeoGebra. It's pretty cool, but again, it's tricky. And, you know, we have to talk about different families of shapes, spheres, paraboloids, hyperbolas, all that kind of stuff. And it's not just that it's a remote course, it's just that it doesn't, in this applied math class, we're more interested in what kinds of stuff we do with functions of two or more variables. So here's an example of one that we're going to probably be using in the future. It's called the Cobb-Douglas function, and it measures a company's quantity of output, Q, based on its capital investment, so how much initial investment money we're putting into it, and the size of its labor force. Now you can measure that labor force in total people or total labor hours or even total machine hours, something like that. I think this thing actually won the Nobel Prize for economics. So Monsieurs Cobb and Douglas did. Here's what it looks like. I know it looks complicated, but we'll see an example. It's not that bad. It's of the form, so Q is a function of K and L, There's a little A and there's another little alpha in there. So K is the capital investment, L is the size of the labor force. A is just some constant that's in there based on like a scaling based on the size of the company. And then alpha is another constant that's between 0 and 1. So what you're going to see is they're both like decimals that are between 0 and 1. And like if one gets bigger, the other one gets smaller. That's how the Cobb-Douglas function works. So A and alpha are not variables. K and L are independent variables. So here's an example. Okay, a company's production for a company's output for Q units of a product is given by Q equals 70 times K to the 0.6, L to the 0.4. Okay, so there's only two independent variables there, K and L. So that's a function of two variables. Those things can change, and as those different stuff happens to those numbers, as they go up, down, whatever, Q goes up and down. So if they both go up, Q probably goes up. If they both go down, Q probably goes down. But if one goes up and the other one goes down, and vice versa, we're interested in seeing what happens there. But for right now, we're just kind of playing around with it. We're not really doing any calculus with it today. Okay, so yeah, the units are K is in dollars, and then L is in labor hours. So just to find a value of a function of two variables is just like finding the value of a function of one variable. You're just sticking those numbers in. So I'm just asking you to stick 100,000 in for K and 1,024 in for L. That's going to give you some number, and then I want you to be able to explain to me what those figures mean. So it's just 70 times 100,000 to the 0.6 times 1,024 to the 0.4. Calculator. That's 1,120,000. So all that means is if I sink $100,000 of capital investment into my company, and I also use 1,024 labor hours, Q is in units of a product, I am going to make 1,120,000 of my product. Right, so that's what that means. So now instead of just being dependent on one thing, it's being dependent on two things. And that's why we're not looking at the graph of this thing, because it'd be a 3D graph. If we hold one of the variables, if one of the variables remains constant, let's think about that. Now it's not varying, so now really Q is just a function of one of the variables. So in other words, if we just hold our capital investment where it was at 100,000, then what does this function look like? We'll just stick 100,000 in for K, and then we can simplify that. That's 70,000 L to the 0.4. That's a 0.4. Hopefully you can see that. So now we just have Q as a function of one thing. So let's look at that graph. And it seems intuitive that, okay, if we keep the capital investment fixed and just have more and more and more and more labor hours, we're probably going to turn out more product. But at some point, it's not just going to keep going up forever. So that's what that looks like. So as L is like the x-axis there, as that goes up, Q certainly is going up if we hold K fixed. But it's not just like shooting up forever. So it starts to taper off. So you get to kind of a diminishing returns thing where maybe you want to, give your employees a day off and invest some more capital. Okay, so we'll return to those types of functions because that's a very useful function of two variables in econ. Here's another one. The satisfaction derived by a consumer from the consumption of two goods, X and Y, is called utility. So I don't know, X is peanut butter, Y is jelly. What if I buy like 10 things of peanut butter and only one thing of jelly? I'm not going to be satisfied because I'm only going to be able to make a couple sandwiches. So I'm just making one up. And as far as how do we measure satisfaction, well, we would assume we have some sort of a consumer ranking scale where they're rating their general experience from, 1 to 100 or whatever. You're giving it a letter grade. Okay, so that's a function of two variables. However many X's I buy and however many Y's I buy, and my level of satisfaction is called my utility. That's how we would write it with our new notation, right? U of xy, and now I'm just making one up, equals x squared y. Let's say we did a study, and that's what we found that people's level of satisfaction with buying, x units of one thing and y units of another thing. So it's like x goes up and y goes down, u is going to go back and forth and stuff too. So we're just going to ask some questions about this. So this is a specific one. This isn't a general, this isn't like always how it works. That's just a specific one I made up. Let's say our consumer here purchases 4 units of x and 3 units of y. So what does that mean? It means this consumer's utility is going to equal 4 squared times 3, which is 48. So now part A of the actual questions. If the consumer instead purchased 12 units of y, right? We went nuts with the y. We got 12 instead of 3. How many units of x would they have to purchase to achieve the exact same utility, to have the same equivalent experience? We have to do a little bit of math, but it's not hard math yet. I already said this, but u of the original quantity, 4 and 3, is 4 squared times 3, which is 48. If we up y to 12, but we want u to be the same, we have 48 is x squared times 12 now. So x is going to go down, right? If we buy more of y, we can buy less of x. Easy math, so x is 2. The answer -2 makes no sense there, as it usually doesn't in these. Definition. The graph of all points x, y that give the same level of utility is called an indifference curve. So in other words, think of the two points we just talked about. Okay, 4, 3. If x is 4 and y is 3, we get a utility of 48. If x is 2 and y is 12, we also get a utility of 48. So you kind of get the feeling that there's like a infinite family of curves that satisfy this thing. Or infinite family of points that would also give you a utility of 48. Now, it might not make sense for x and y to be decimals, but maybe they could be, right? It wouldn't have to be like a discrete quantity. So if you graph all those together on the same xy plane, that's called an indifference curve. And in general, this is important because these curves are also called contours, and it's how we can make something called a contour map. Picture like a topographical map of a mountain. That's a 2D thing that gives you an idea of what a 3D shape looks like. So it's a very useful tool in visualizing three-dimensional shapes. So here's what they look like. So there's that, what we call an indifference curve, or we call it just a contour of the original function, u equals x squared y. Notice the point 212 I marked off is on there, and the point 43 is on there, right? So those are two different combinations for x and y that give the same value for u. What else? The point 5, a little less than 2, is on there. So 5 squared times 2 is 50. So 5 squared times a little bit less than 2 is going to be 48. Okay, so we're interested in graphing a bunch of these curves together because that gives what's generally called a contour map, but in this particular instance, they call an indifference map. So if we graph a set of indifference curves for the same utility function, but that give a bunch of different levels of utility, you'll see in a second, that's called an indifference map. So here's one. There you go. Those are the indifference curves for, I just randomly picked u equals 12, 24, 36, and 48. So for every one of those curves, no matter where you are along any one of the specific lines, you're getting the same value for u. You're getting either 12, 24, 36, or 48. And I wish there was a way to superimpose this. There is a way, but it's hard. Underneath the graph, the 3D graph of u of xy. You see what I mean? This kind of gives you the visualization of a 3D shape that kind of goes up like that. Maybe I'll attach some animations to one of these. Again, it's not really important for us. It's just cool. It just looks cool. So we'll return to that idea in the future of doing like different sort of contours and different levels for functions of two variables, because I do like the visualizations. So as we start to do derivatives and calculus with this stuff, we'll just return to utility functions and Douglas Cobb functions probably a lot.